We're going to finish up the little section on transition metal isomers and different types of isomers that you can have, and how you know the difference chemically between the different kinds of isomers. I will point out that this got covered in lecture, so I will not be covering it again. We talked about cis and trans, and we talked about also optical isomers, or when you have two of them, enantiomers, and we didn't mention distereomers, but there's yet another class. But we did talk about that, and I showed you how to draw those in lecture, so hopefully you're okay with that. Now, so let's get on with this lecture. There's under structural isomers. Now remember, isomers all have the same chemical formula, but their structures, their specific structures, are different. And now in stereoisomers, just to go back on that a little bit, stereoisomers, the central atoms are the same, but it's the arrangement of the ligands around the central atoms that are different. So one type of isomerism is a ligand swap. That is, you take a ligand from from the coordination complex ion. So this is a formula of a coordination compound. You take a ligand for one of them, right? Or maybe like a ligand here, and you swap it with what was otherwise just the sulfate ion on the outside. So you're actually bringing something outside the sphere of the complex ion. So let's think about this as being in a sphere of a complex ion. So it's an octahedral complex with 6 ligands. And then what you do is you take one of the ligands and you replace it with the anion on the outside, and you would bring that in like this, and then the bromine, and then you end up with this. And this is known as an ionization isomer. It's the ion switch place. Now, when we talk about complex ions, one of the things that you need to understand is those formation constants that we talked about before are very high, and so the ligands themselves are not easily displaced, and so the ion, in this case sulfate, on this compound is free to when it's dissolved to roam about the solution away from the complex ion. In this particular coordination compound, the bromide is free to leave, and so you'd have different kinds of chemistries with bromides and sulfates, which maybe would help you distinguish between these two. So if you, for example, react this compound with barium nitrate, you will get a precipitate, and while this one does not, and you need to explain that. So for example, when COBrNH3 5 goes into solution, what will happen is these things will break up, and so you'll have the complex ion over here, and then you'll have sulfate over here. And then when you bring that in contact with barium, barium sulfate is insoluble, so you get barium sulfate as the precipitate. Turns out barium bromide is not insoluble, so when you put this compound in solution and you get bromide ion out of it, and then you react it with barium 2+, that's a no reaction, so you get nothing coming out of it. So the explanation is barium bromide is not insoluble while barium sulfate is, and so that's the distinction between these two compounds. Another kind of isomer is known as a hydrate isomer, and in a hydrate isomer you have water on the outside of the sphere, for example, and it will displace a ligand or exchange with that ligand, and that's known as a hydrate isomer. If you'll notice, this compound has 6 waters and 3 chlorides in it. Whereas this compound also has 6 waters and 3 chlorides, so they all represent different compounds with varying amounts of chloride free to dissolve into the solution when that compound dissolves. And if you remember hydrates, the waters are just part of the crystal structure. So the actual formula for the complex ion, these complex ions will have different masses because of the different amounts of water and chloride incorporated in the complex ion. So how would you distinguish if, for example, you treated these three complex ions with silver nitrate? How would these three coordination compounds differ in the amount of precipitate that was formed? Well, for this one, you would get 3 Cl minuses, and for this one, you would get 2 Cl minuses, and for this one, you would get 1 Cl minus. So this would make the most precipitate because as you add Ag and, oops, didn't need a bracket, AgNO3 to C to solution. This is soluble, so this is aqueous. What you free up is you free up Ag plus, and when that meets a Cl minus, solubility rules tell us this is a precipitate, and the amount of precipitate you get for the same mass of compound will vary. The most coming from the first compound and the least coming from the last compound. Ooh. Another kind of isomer, I don't know why they zoom that way, is known as a linkage isomer. And in a linkage isomer, the ligand attaches on one end or the other. So thiocyanato, remember if you've watched the nomenclature lecture, you put an O at the end at negatively charged ions. Or isothiocyanato, that means in thiocyanato it's connected through the sulfur, and iso just means isomer of thiocyanato. So you flip it around and you connect it through the nitrogen. Another common ligand that does something like this is the nitro ligand. And if I could just skeletally drawn like that, this is nitro when it bonds to the metal if through the N, and if that's nitro, sorry. And then if the metal bonds through the oxygen like that, this is a nitrito. So how you know which end is bonded requires some spectroscopic techniques to tell bond strengths and what's bonded to what. You guys don't have that exposure, but just so you know, there's like this SCN ligand can be bonded two different ways, just like the nitro and the nitrito ion can be bonded. The last one of these isomers is known as a coordination isomer. So you have a coordination compound consisting of two complex ions. And they, if you take a ligand from here and swap it with the ligand from there, you can form compounds that look like this. So that's all that's happened. If you count the NH3s in up here, there's 6. And if you count the CNs here, there's 6. There's 5. And then 1, right here. 1. And then the CNs, there's 5 and there's 1, so it's still the same total number, but what's happened is those complex ions have, if you think about the sphere again, have taken a ligand out of their coordination sphere and exchanged it with the other complex ion. So in a nutshell, that is the rest of the isomers for transition metals. We talked about ionization isomers, which exchange one of the ligands with one of the anions or the cations on the outside. There's the hydrate isomers where you exchange a water molecule. There's a linkage isomer where the molecule that's the ligand can be flipped and bonded through one atom or another atom from the same ligand. And then there's coordination isomers where two complex ions exchange ligands to form a different coordination compound. So now we come to a rather interesting topic. it's one of the ones that's oddly enough important in sort of the way you think for what you're going to be getting into when you get into organic chemistry. And that's stereoisomerism. Stereoisomers are one of the important topics for both like organic chemistry, but also medicine and biology, because it turns out there are lots of compounds that have the same ligands attached, or the same atoms attached, in the case that you'll cover in organic chemistry, but they actually have different spatial arrangements. They have different spatial shapes. So we think about this, the way we often say it is we look at our hands and we say our hands are like stereoisomers. They each have components of thumb and four fingers, hopefully, and then but when you try to look at your hands, you'll notice they're not the same because they're actually mirror images of each other. And this is where the idea of stereoisomerism comes from. It's like a stereo picture, like you see both sides, okay? So how do we talk about the arrangement in space? And it turns out in complex ions, we have a couple of different ways at least. There's cis and trans, which means same side, opposite side. Or fac and mer. So what that means is it's on the same face, and I'll explain these. That's where the term comes. Or they're on the meridian. The meridian's the middle. And then there's this whole topic of optical isomers, and these are actually mirror image structures. And you can kind of imagine that it gets its name because they're mirror images. You know, that kind of makes sense because it's optical, right? But in fact, they get their name because the way optical isomers interact with everything is the same except for light. They have the ability to turn the polarization of light in one direction or the other depending on which optical isomer you have. So let's go into each one of these in a little more detail. So here's a platinum complex ion, square planar arrangement. And this is what we mean by cis. They're on the same side of the platinum atom, and this one is trans. And what you'll notice is the cis-trans isomers, the different arrangements, actually cause them to be chemically different. That is, their physical properties will be very different. This one would be polar, this one would be nonpolar, for example, because the electronegativities would exactly cancel on opposite sides. So cis and trans isomers are chemically, structurally different compounds. That is, if you wanted to, you can isolate these based on their physical properties because those physical properties are different, okay? Here's another, at the bottom, another example of cis and trans. We have trans right here, and then we have cis over here. And you notice I drew it a couple of different ways. This is cis as well, and this is trans as well. And it turns out these are the same compounds. So, for example, these two are the same. And then these two are the same. Now they don't look the same because the molecules are oriented differently. It makes it even harder that we're using this plane in the middle because it makes you think that that always has to be flat, right? But the plane will stay even if you rotate the molecule because we're just trying to indicate which ones are out in the front and out in the back. So if I take this molecule and I rotate, let me change the color so it doesn't get too confusing. I rotate this one down, right, and then this one up like that. You'll notice how these two would represent the same molecules. The NH3s would still be the same on the ends over here and here. Use a laser pointer instead. So yeah, these ends, right, would rotate up, and this one would rotate down. So that's what I'm showing here and here. But these groups would stay in place. That's where it would be pivoting, right? And what would happen is these two would then be the same. These two are also the same. The transformation is a little bit more complicated, but it's just another rotation. So if I take, for example, this chlorine and I rotate it this way, right, and this NH3 and I rotate it this way, then what happens is this chlorine and this nitrogen, ammonia group, but the nitrogen stay in place as you pivot the molecule, and then you end up putting this chlorine down to here, and this amine group over to here, and this one up to here, and that's actually, right, this, sorry, I think I said that backwards. That's actually this structure. I think I said that right, but you get the idea. It's just a rotation. One of the tasks that you'll have on your take-home is to take a formula for a complex ion and draw all the unique structures that you can. This is actually a really valuable skill for visualization, it turns out, when you take organic chemistry. Let's take a look at FAC and MER. So you notice this is what you'll get anytime you have two ligands that are different than the rest. And then what happens if you get 3 and 3, right? So if you have 3 and 3, then this is the possible arrangements that you can have. Now, you'll notice the formulas got jacked up. Sorry. You'll notice they're kind of screwed up. It says NH3, so these are NO2 minuses. Anyways, yeah. So what's happening on this, though, is you see the NH3s are all in one plane, right? This one, the NH3s, are all in two different planes. There's one going this way and one going this way, like that. So this is FAC. It's all on one face, and this is MER. It's all around the meridian, around the middle on one direction. So these two are unique compounds. So I was just realizing as I was going to say that this was the name of this compound, you notice the nitro or nitrito groups are missing. Nitrito is if it's connected through the nitrogen, but I can't quite tell because anyways, it doesn't matter. But this would be also known as cis when they're all together on one side, but this is also known as FAC. And this would be trans because they're on planes where two of them are always opposite of each other. These are opposite of here, and these are opposites of here. So this name is essentially right for the amine, but it's missing the trinitrito or nitro in here, depending on how it's connected. Anyways, and it would sit like right that trinitrito or nitro would be here. Alright, so it's a little bit different. I'm going to try to insert this video. That's my hand, of course. And I'm going to show you the mirror image of my hand. That would be my other hand. I know they're mirror images because when I set them in front of each other like this, opposites, just like when you're looking, if this was you and you were looking into a mirror, that's what you would see, right? Here's the deal about mirror image hands. They're not the same because you can't superimpose them. Yeah, so mirror image hands, right? Non-superimposable. And this is what sets up the idea of optical isomers. We call it chirality. It's known as handedness. The word chiral comes from the Latin for hand. But there are objects that are not, whose mirror images are not different. So here we go. I have two binder clips, right? And the binder clips are mirror images of each other. But here's the thing. They're exactly the same. That is, they're superimposable. You could take one binder clip and superimpose it over the other, or you could be looking at one, right, and not be able to tell it from the other because shape-wise, they're exactly the same. So there's something special, right, about our hands that allow them to have this property of chirality. That is, I have a left hand and I have a right hand, right? Binder clips are achiral. I'll write these words down on the board, on the screen. Are achiral because the left hand and the right hand, right, are the same. So really, there's only one-handedness to it. And just a bit of advice, don't look up mirror image hands. I made the mistake. If you want to and you're not easily grossed out, then you're probably all good. So when we talk again, some of the words, mirror image, chiral, this is one of the important words. These are non-superimpose. Ran out of room. Hang on. There we go. So non-superimposable. So non-superimposable mirror images gives us chirality. So we can say a compound is chiral if it possesses a non-superimposable mirror image, which means if you take the mirror image of it, it doesn't superimpose. So now, from this, what we get, though, is we get a pair of compounds. So using sort of the transition metal theme, I have 4 different groups here. This is the idea, 4 different groups. Now, it doesn't mean to say that I have 4 groups, right? I have 4 different groups. I have the groups A, I have the group B, C, D, and then the same thing, I made the mirror image of it. Now, you can see if you draw the plane of symmetry, I essentially just drew this structure, right, backwards from this one. If these are non-superimposable mirror images, then what happens is these are chiral, and the pair of them, right, are enantiomers of each other. So these are enantiomers, right? The word is enantiomer. And an enantiomer refers to one of the 2 compounds, the left-handed or the right-handed molecule. Now, we're not going to go into the nomenclature of designating which one's left and right, because that's a little bit more than we need to do. But I wanted to get the idea that these are non-superimposable mirror images. Okay, so how would I go about making that determination, right?